In fact, this is an example of what's called an Euler equation, and for this there is a standard substitution. And the substitution we make is that x equals e to the t, and you'll see how this is useful as we progress. Now, before we start, in order to use this substitution, when I come to actually make the substitution, I'm going to need the derivative dx by dt, which actually is just e to the t again. And in fact, more importantly, you'll see I'm going to need dt by dx, which is 1 over dx by dt. So that is e to the minus t. And that's going to be useful in a minute. So what I'm going to try and do here is replace the dy by dx and the d2y by dx squared with expressions involving t. And in order to do that, I'll work on the dy by dx first. I'm going to use the chain rule. So dy by dx is dy by dt times dt by dx. And you can see that I've already got an expression for dt by dx above. So what I have is dy by dt multiplied by e to the minus t. And it's that boxed expression that is going to go in place of the dy by dx when I come to make my substitution. So what I'm now going to do is look at d2y by dx squared, and this is a little bit more complicated. What d2y by dx squared is d by dx of dy by dx. So in our case, dy by dx is what's in that red box above. It's dy by dt multiplied by e to the minus t. And what you should notice is that what's in that bracket there is actually a function of t. And so again, I'm now going to use the chain rule. Instead of differentiating that with respect to x, I'm going to differentiate it with respect to t and then multiply by dt by dx. So I've got two separate terms here. The first term is d by dt of a product. So I'm going to use the product rule to differentiate it. Differentiate the first, write down the second, plus write down the first and differentiate the second. And then I've got to multiply that by the dt by dx at the end, and dt by dx, if you remember from above, is e to the minus t. So let me just simplify this. I've got d2y by dt squared, and I've got an e to the minus t multiplied by another e to the minus t, so that's an e to the minus 2t, and similarly with the dy by dt. So that whole expression is equal to d2y by dx squared, and if we go back up you can see where it's going to be inserted. I'm going to be replacing this term here by it. So let me now go back down and write out that differential equation again so that you can see what I'm doing. What we had before was 3x squared d2y by dt squared minus x, we had 3x squared times by d2y by dx squared minus x dy by dx plus y equals 0. And what I've made the substitution is I've used x equals e to the t, and with that substitution it's going to become something different, and the idea is that we're going to have a simpler differential equation once we've finished. So let me now start writing out this differential equation, making the substitutions as I go. So what I have first is 3, then I have x squared, and then instead of d2y by dx squared I've got what's just disappeared off the top of the screencast, but my screen isn't quite big enough, but I've got it written down by the side here. So what I had was actually d2y by dt squared e to the minus 2t, and then a minus dy by dt e to the minus 2t. So that's that whole 3x squared d2y by dx squared term. I now also have minus x, which is e to the t, multiplied by dy by dt, and that has disappeared, but I did make a note of it, and you may be able to remember what it was. It was dy by dt times e to the minus t. So I've replaced the first two terms, and now I've just simply got a plus y equals 0. And the idea is that this should now simplify considerably, and hopefully you can see that that's true. What I have here is an e to the 2t, and it's going to cancel with the e to the minus 2t. What I end up there when I multiply those two terms together is e to the 0, which is 1. So that the first term becomes 3 d2y by dt squared minus 3 dy by dt. Then the same thing happens with the next term. What I've got here is an e to the t and an e to the minus t, so that they cancel, and I'm just left with another minus dy by dt. Plus my y at the end equals 0, so that I end up with a constant coefficient linear second order differential equation. And this differential equation is far simpler to solve than the original nonlinear one. You notice, in fact, this differential equation is homogeneous. There is no function of t on the right-hand side here. I've just got a 0. That's fine. Had I had a function of t here, that would just stay, and then when I came to solve at this stage, I would have a particular integral coming through. But in fact, in this case, all I have is the complementary function, because I just have 0 on the right-hand side. So proceeding as before, the auxiliary equation is 3 lambda squared minus 4 lambda plus 1, which equals 0. Factorising in this case, I think it will factorise, yes, 3 lambda minus 1 and lambda minus 1 equals 0. So lambda is 1 or a third. And the important thing to remember is that this differential equation that we are solving at the moment has y in terms of t. And so when I write my complementary function, which is in fact the general solution, it's going to be y in terms of t. So I've got a e to the 1t plus b e to the third t, where a and b are arbitrary constants. And finally, I substitute back. So with x equals e to the t, if I have, for example, e to the third t, that is e to the t to the third, which is x to the third. So the general solution ends up being ax plus bx to the 1/3. And that's the general solution, because the constants a and b have not been found. If we were given either initial conditions or boundary conditions, we would be able to find a and b.